we've been kind of obsessed with water lately, and water's hydrogen bonding and its solubility. And so we're really familiar with this polar water molecule by now, where because of the high electronegativity of oxygen, the electrons in this bond between hydrogen and oxygen are pulled up toward the oxygen. If electrons are being pulled toward the oxygen, and the fact that there's electron pairs on oxygen, it makes that oxygen region of a water molecule pretty negative, leaving the hydrogens lacking the electrons and partial positive. So we know that water molecules themselves are very attracted to each other with these hydrogen bonds, which are really an intermolecular attraction and not necessarily like a covalent or ionic bond. It's an attraction between the molecules, where the negative oxygen end of one molecule is attracted to the positive hydrogen end of a neighboring molecule. It affects things like phase and melting point, boiling point, solubility, which is kind of where 32 is going. Water, H2O, is liquid at room temperature, while carbon dioxide is a gas. What's different about their structures that results in very different properties? And so it probably has something to do with the polarity of the molecule, right? In that water has polar bonds. I mean, both of them have oxygen, and oxygen has a really high electronegativity and pulls on the electrons and pulls on the electrons. But because the water molecule is bent, these little poles are not evenly distributed around the center. And so we get this net draw for the electrons to be up toward the oxygen. Partial negative. The hydrogens are lacking electrons and become partial positive. This is bent and polar. A polar molecule. A little bit different is the carbon dioxide molecule, and both of these are dot structures that we've drawn a bazillion times, but often in determining the structure of a substance, it's going to help to draw out the little dot structure, and then we'll do like what we did in the last unit, look at the arrangement and the number of electron groups on the center. So here in carbon dioxide, I have 2 electron groups on the center. They're both double bonds, so there's 2 groups of electrons, and it just happens that each group of electrons involves 4 electrons. Carbon and oxygen do not share the electrons equally. Oxygen has a higher electronegativity. It's closer to fluorine. Oxygen already has 6 valence electrons, and he's really close to getting his octet 8. So if oxygen pulls on the electrons, but there's another oxygen pulling with the same force in the opposite direction, now because these 2 bonds are arranged equally around the central atom, this molecule is linear. Whoopsies, linear. And linear molecules, as long as both atoms on the outside are the same, will have their little poles cancel. And we have a nonpolar molecule. Well, nonpolar molecules are only attracted to each other by dispersion forces. Dispersion forces. Where maybe just by chance those electrons on carbon are moving in a way that for a moment in time puts them not equally distributed around the center. Well, then I could get a partial charge, but it would be very temporary and short-lived. But with the water molecule, I'm always going to have the partial positive and partial negative charges. And in fact, it's a pretty intense positive and negative charge because oxygen has a really high electronegativity and hydrogen only has 1 electron. So here we'd have the hydrogen bonds. Really polar regions that are very attracted to each other. And so yeah, it's just that the water molecules have stronger attractive forces. So it's more likely then that they would be close to each other in the liquid phase. With weaker attractive forces, it's more likely that the carbon dioxide molecules are in the gas phase. And so one other kind of unique property of hydrogen bonding then is surface tension, where we've seen like leaves on a swimming pool and they don't sink to the bottom, or little bugs can walk across water without sinking to the bottom. Or maybe we've seen water kind of beat up on the leaves of a plant. That's surface tension. It's where water kind of forms these little droplets. And it's because of hydrogen bonding. And so what happens is that the water molecules are really attracted to themselves, because all the water molecules have these partial positive and partial negative charges. But on the surface of the water, I mean, this would be maybe like air up in here, or maybe it's the surface of a leaf or something like that. It probably doesn't have a lot of charge to it. And so the water molecules are attracted to themselves, but they're not really attracted to air or like the surface of a leaf. And so then that just kind of enhances the attraction between the water molecules themselves. These particles on the surface are really only attracted to the other molecules of water that it's in contact with, but they're not attracted to the air or whatever's above it. So you kind of get this inward attraction between these water molecules, and eventually it kind of forms a bead, or this like three-dimensional droplet, where the water molecules on the surface are really only attracted to each other. And they kind of almost form like a film, where it's like this coating that seems to be like a tough coating that is why bugs can walk across water and leaves can lay on the top of the water surface. Well, it's really nothing special. It's still just a bunch of water molecules. They just become a little bit more strongly attracted to each other because they're not attracted to what's on the top. Now, the degree of attraction between the water molecules might also depend on the surface that they're sitting on. So if I have a bead of water and I put it on a non-polar substance, well, obviously then the water molecules are very polar, and the non-polar substance would not have a significant charge to it. So now the water molecules become more attracted to themselves and not so attracted to the non-polar surface. So you'll notice that there's not as much surface area where the water is actually touching the non-polar surface. It's more likely that the water molecules form this bead, and they're more likely to touch each other. Whereas if I have a polar surface, it's more likely that the water molecules will not only attract each other, but they'll also be attracted to the surface that they're sitting on. And so now you'll see like your bead of water kind of flatten. And there is a little more surface area between the substance, like the surface, and the water molecule. Where here when the surface was nonpolar, there really wasn't as much water touching the nonpolar surface. The water molecules are more attracted to themselves. But if they're on a surface that's also polar, then the water will spread out a little bit. And we say that the water makes the surface wet, which just means that the water is spread out amongst the surface, as opposed to the water just forming little like beads or little droplets that don't completely cover the surface. They kind of stay in their little water droplets. They're not so attracted to the non-polar surface like they would be a polar surface. Interesting. And so what if we want the water to spread out? We want something to become wet. Or what if we want something like an oil or a fat or a grease? What if we want that to be washed away by the water? But we know that like dissolves like. So polar water molecules would not be attracted to non-polar molecules like oils and greases and fats. But yet somehow we need to use water to clean our greasy fingers or an oily pot. And so instead, soaps and detergents contain something called a surfactant. And they kind of have this section in the middle here that's somewhat important. It's a good explanation of a surfactant. So these are usually like pretty sophisticated molecules. They're really big molecules that have two regions connected to each other. There's usually a polar region, and often that's called the head. And then there's a nonpolar region to the surfactant molecule, and that's called the tail. And so both charges, or should say both polar and nonpolar components, are put together in a surfactant molecule. And so they're like pretty sophisticated compounds. They're pretty big compounds. They've got a polar region and a nonpolar region. Okay, so these are present in soap and detergent. And here's kind of what happens. And the polar water molecules will be attracted to the polar end of the surfactant molecule that's in your dish soap, for example. And so that allows these surfactant molecules to kind of mix in with the water, and it breaks the surface tension. This polar head region, you can kind of see that, kind of down in here. Like that polar head region is attracted to the water molecule. So the water molecules separate a little bit and let in these surfactant molecules. But it has to be in the proper orientation. It's the polar end of the surfactant that's allowed onto the surface of the water. Now again, because that kind of breaks the surface tension, it allows the water molecule to spread out instead of just forming a bead. So right there, our surface becomes more wet because the water will spread out among the surface. But now enter in like a fat or a grease or an oil. And so here on the bottom is the polar region of the surfactant. And then on the top, this would be the nonpolar region. Well, it's almost like these surfactant molecules become like a connector between the polar water and a nonpolar oil, where the polar end can attach to the water molecules. It kind of attracts itself to the water molecules, but then the nonpolar end of the surfactant would be attracted to a nonpolar molecule like an oil or a fat or a grease. Well, again, then these surfactant molecules kind of link the water to the oil or grease, which then does let me rinse away the grease with extra water. Ah, interesting. And so here in 33, they're talking about printer ink. It says printers often use surfactants in the printing of paper with ink. Explain why this might be. Well, often inks are either polar or nonpolar. It kind of depends. Like your Crayola washable markers and pens would have a polar ink, because then that can just be washed with water, polar water. But a lot of your permanent inks and permanent markers are nonpolar molecules. And so nonpolar molecules are more attracted to each other. Polar molecules are more attracted to each other. So these surfactants are added to the ink so that when you write, the ink doesn't just bead up, that the ink spreads. That as I draw a line on my paper with the ink, it'll spread out amongst that line that I drew, and instead of just making a big clump, that now the ink is more likely to spread out, as the surfactants can be attracted to either polar molecules or nonpolar molecules, but they'll kind of attract themselves in the right orientation and break that surface tension so that the ink then can spread more easily.